Welcome everyone to the second talk this morning. So it's my great pleasure to introduce the next speaker, Gabriele Benedetti. He's going to tell us about localization of closed magnetic geodesics for low energy.
Thank you very much for the introduction. Thank you very much for the introduction, Sylvia, and thank you to the organizers for having me here. So it's really special to be the 10th edition of this workshop. I was here first time in 2013 as a PhD student, and it was great to see all the faces behind the theorems, and also had a good time sharing the room with Jean Gut over there, and Skyping with his cat, Zoe, I think it was called, yeah. So for me it's really special then to be here to give this talk today. I'm going to talk about a recent work in progress with Valeria Senza and Leonardo Maccarini from IMPA. The talk will be about closed magnetic geodesics. So magnetic geodesics are the formation of standard geodesics. So therefore, the problem of existence of closed magnetic geodesics is really important. But for low energies, actually, the behavior of magnetic geodesics will be kind of very different from the one of standard geodesics. In particular, we will see that the motion gets localized very much, and therefore it's meaningful to ask where can I find on my manifold these closed magnetic geodesics. No? So if there is a way of kind of from geometric features saying, okay, my closed magnetic geodesic will be here rather than there, no? And this is why we talk here about localization. And this problem is also important if you're just interested in the purely existence problem, because it allows you also to get some new results, even for non-compact manifolds. So that's also why we're interested in this problem. And probably I will not be here today giving this talk if it was not for the work of Gonzalo and Will, so I dedicate the talk to them. Okay, so let me start with setting up the stage and the setting. And at any time, if there is any question, feel free to stop me. Okay, so the setting is Q is a manifold for us without boundary. And you can think of Q both as compact or non-compact, possibly non-compact. Okay, so now I want to define magnetic geodesics, so I need a manifold, I need a metric, G, Riemannian metric on Q. And then I need a magnetic field, I call it beta. This is a closed two-form on Q. And then with this data, I can define the Lorentz force. I call it capital B. This is an endomorphism, linear endomorphism of the tangent bundle, which is the representative endomorphism of beta with respect to G. No? So then this is defined as I take beta at the point Q, and then paired with two tangent vectors. This should be G, and then you have B applied to U, inner product with V. Okay, so this is a linear endomorphism, and from the fact that beta is antisymmetric, then B is also antisymmetric. Okay, so with this data, I can define now the magnetic geodesics. So Q from R into capital Q is a magnetic geodesic if it satisfies the equation acceleration equal to the Lorentz force. And this is a nice second order ODE, but it has a lift to the cotangent bundle as a Hamiltonian system, and that's why we have many powerful techniques. So magnetic geodesics lifts to the cotangent bundle. Or lift on the cotangent bundle to Hamiltonian flow lines. of H, the kinetic energy, with respect to the twisted symplectic form. So this omega sigma is the standard symplectic form minus pi star beta. Omega beta. Yeah, omega beta. Okay, so that's why we are interested in this setting. And also, as you see from here, this part basically is quadratic in the velocity. This is linear. So for high energy, so energy is basically just the speed. So for high speed, this is the dominant term. So you just see the perturbation of geodesics. So for high energy, is a perturbation of geodesics. While for low energy, this is our focus today, you have some sort of localization phenomenon. So, and let's have a look at this in the example of surfaces, which will be important also to motivate our main theorem later. So in this first example, Q is just an oriented surface. And then in this case, beta is just a function, b times the area form. So this b now is just a function. And you have the fundamental property that Q is a magnetic geodesic with speed s, if and only if the geodesic curvature of Q is b of Q divided by s, and yeah, of course, Q dot, again, this must be equal to s. Okay, so on surfaces, basically, you are looking at curves of prescribed geodesic curvature, and therefore this is also a problem that's very interesting for people doing geometric analysis. And the most basic cases that you can think of are those that I already drawn on the blackboard over there. So the basic case is when when b is constant, different from 0, and then the Gauss curvature is also constant. Now this is the Gauss curvature, and then what happens if you look on the on this blackboard? Then you have the three model geometries, and then there is always kind of a threshold below which all orbits are closed. No? So here, for instance, they are kind of circles in the case of the sphere, and when the speed goes to infinity, they approach standard geodesics. Similarly here for the case of R2. In this case, you get a circle, and you can even write down the radius of the circle is something like the speed divided by b0. That's the radius. And then for the hyperbolic plane, you have like a critical value called Magnier critical value as 0, and then below you have circles. Here you have the orocycle, which is kind of tangent at infinity. And then above you have dynamics very similar to the one of the standard geodesic flow. So here is kind of anosov and chaotic. Here is regular, and there is kind of this transition phase. Okay, so what we see here is that for low energy, for low speed, then the motion is kind of very concentrated and regular. And we can understand this also if we go and look a bit beyond these basic cases. So if I now take a case where B is not constant, no, so now if B is not constant, then I can have a look at low speed, which means that I look at points where B over S, S over B is very small. Then what I can look at a regular energy level of B. So let's think that this is like a regular energy level, let's say, of even the modulus of B equal to C. And then my magnetic geodesics will kind of spiral around this energy level. No? So this is my magnetic geodesic Q. No? So it tends to concentrate around this. And here you see that this is kind of true when this is a regular energy level. But then you can imagine that something now must happen when you reach, for instance, a local maximum. No? So imagine this here is a local max of the absolute value. No? So then here you see that in some sense this goes around very fast, but then also the energy level kind of is short. So what you will find here will be a short, so there exists kind of a short periodic magnetic geodesic, like around local max of B. This is like a theorem that goes back to the work of Victor Ginsburg. And it's like a very nice theorem on the case of surfaces that tells us that in this case we are expected to find these orbits close to the local maxima of the absolute value. Okay, now what we want to do, we want to explore this phenomenon also in higher dimension. Any question? Okay, so before we go and study general case, let's have a look at one easy example in higher dimension. Okay, this is, I call it example 2. So now we are in higher dimension. Let's take a look at the case where Q is just a Euclidean space and G is just constant, call it G star, and also beta is just constant. Beta star. So this is all constant. Okay, so now in this case, the Lorentz force is just an antisymmetric matrix, so I can diagonalize it over the complex numbers. So then B star will be a bunch of rotations. A bunch of 90 degrees rotation up to scaling. So IB1 plus IB2 plus IBK, and then possibly some zero also, some kernel. Okay, so here I can also make this in such a way that B1 is the biggest, and then you have all this. BK is the smallest, and these are all the positive ones. Right, and then if I look now, right, and then this B1, I can also imagine it as basically the norm of this endomorphism. So then this B1 is also the norm of this B star, which is also the norm of the two form, basically. Okay, and now if I look at the solutions of this, the magnetic geodesics in this case, I have Q0 equals some Q star, Q dot 0 equals some V star, and this V star I can decompose it in this according to the splitting. Then you have some U. Okay, then the magnetic geodesic will be something of the type Q star, and then you have plus some rotations. So this is e to the I B1t minus 1 over I V1 over B1, and then you sum over all over all components, and then the last one is just a straight line motion, no? So T, TU. No? So these are kind of circles of radius, this guy here, V1 over B1, and this is just a straight line. Okay, so here you see a lot of, in the case where this is different from 0, no? So this is an interesting case. You have a lot of kind of periodic motions. Basically, in every component you have one. So this implies that there exists periodic magnetic geodesics. And you can also say something about the period, no? And the minimal period, you see it here, no? When this is the biggest. So T min is 2 pi divided by the absolute value of B1, which you can also rewrite it in terms of this beta. Okay, so this is kind of a simple, very simple case. We understand everything here, but this will also be used in our main theorem, so it's good to keep it in mind. Are there questions about this example? Okay, so let's see in general how we can find periodic orbits, and this is via a variational method. Okay, and here for simplicity, I'm going to assume that beta is exact. Simplicity, beta will be exact. And in this case, I can define a Lagrangian, which just gives me periodic orbits. Then this is 1/2 v squared minus alpha times v. And then if I'm considering just the contractible ones, so this is like contractible loops, I can define the action. So this is, I call it AS. Which is the integral between 0 and t. So here I'm taking loops with arbitrary period, so contractible loops with arbitrary period. And I will denote the period by t. So this is just L plus the energy integrated over q dot. Okay, this is a so-called free period action functional, and then the critical points of this. I know that Q is a magnetic, like contractible magnetic geodesic of speed s, if and only if Q is a critical point of this thing. Okay, so what happens, for instance, let's do like a quick example. What happens to this action in example 1 and 2? So in example 1, I had this. In example 1, I had this short orbit here. Now let me call this QS. This has speed s. No? So maybe I didn't write it here. Like of speed s. So that's the S appearing here. So in example 1, this AS of QS is roughly pi S squared divided by the max of B. And then there is some order term, higher order term. In example 2, then this is again can be more complicated, but the idea is that this is anyway S squared divided by 2, the energy times the period. And therefore, this is always bigger or equal than S squared over 2 times the minimal period, which we wrote over there. So this is then pi S squared over the norm of beta. Yeah. Okay, so in this case, all orbits have positive action, and they also have a bound from below that can be expressed in terms of the speed and in terms of the magnetic field. Okay. So now we have this nice variational principle, but to make it work, you want to assume something about your manifold Q. And for the rest of this section now, I'm going to assume the Q is compact. And then in the third section, I will go back to the general case. So assume Q compact. And I'm going to take now S, which is smaller than the Manier critical value, which is the supremum of all values S prime, such that there exists some Q in the contractible loops having negative A S prime action. Okay, then under this hypothesis, I can define a minimax class. I call it gamma S. So these are paths from 0 to 1 with values in the loop space, which start at the constant loops and end at a loop with negative action. So then an A of AS of gamma 1 is less than 0. Okay, so we always have such a loop, such a path, because we are below the Manier critical value. And what we can see, if we kind of now plot in the interval 0, 1, the function AS composed with gamma, we see that at the beginning, we start basically at 0, then we go a bit up, and then we go to some negative value. And then the idea now is that if you do minimax, you want to kind of push these things down, and there will be like an infimum for this max, which I call it CS. So CS is the inf over gamma in the minimax class, or the max in the interval 0, 1 of AS gamma R. All right, so that's the minimax construction. And now you can say, so basically what you want to do, you want to show that there exists a periodic orbit having action equal to CS. And for this, we recall some facts. Okay, so the first fact is that CS is actually a positive function and is increasing. And then, in general, okay, we don't know much about this function, so it could be also, in principle, non-smooth. But we know something about how this function approaches the behavior of this function when S goes to 0. And what we can say is that this function here is less or equal than pi S squared over the infinity norm, so the max of the norm of beta over Q, plus some higher order terms. Okay, so why do we know this? Because basically what you can do, you can take since now Q is compact, you can take a point realizing this norm of beta. So there will be a point here, Q star, and Q star has the property that Q star, beta of Q star is equal to the max. And also you know that this corresponds to an eigenvalue. Do I have it there? Yeah. No? So this corresponds to like a plane inside your tangent space with a corresponding largest eigenvalue. And so then what you do, you take a class gamma, gamma that is contained in this on this plane. Okay? So then this is the two-plane corresponding to B1. And then your gamma starts here and then takes circles doing like this. Okay, so this is your gamma of R. And then if you do the computation, you will see that this thing here has a maximum, which is roughly this thing. No? Basically a bit for the same reason that you can do the computation on the constant case, and then this will be just some small perturbation of that. Okay, so this also we will need later. Then what are the other things that we know? Well, then we know that if we take, if there is a Pallies-Mills sequence, then we know that there is a Pallies-Mills sequence. There exists some Qn contained in lambda 0 Q with the property that the differential at this Qn is going to 0, and the action at this Qn is converging to CS. And now the crucial point is that if we can guarantee that this is a converging sequence, no? Because if we know that Qn converges to some loop, then this loop will be a critical point of AS with the action given by CS. And we also have an additional information about the Morse index of this thing. So the Morse index of this Q infinity will be equal to 1, because this is like a one-dimensional family. No? So then this kind of is reflected in the information about the index of the minimax orbit. Okay, so the crucial thing is that to have this convergence. Yeah, it could also be 0, yes, in the case. And okay, this would mean, yeah, but it's never a local.
Local margin degree.
Huh?
Yes, local margin degree.
Yeah, yeah. Okay. Then last thing that we want to cite is the fact that the only thing that we need to have this convergence up to subsequence is the boundedness of the period. So if the periods of these orbits are bounded, then up to subsequence, you have the convergence. So the only thing that you want to have is this boundedness of the periods. Here. Okay, and then a theorem by Gonzalo Contreras tells us that this boundedness, you can have it for almost every value of the speed below this Magnet value. This is a very nice theorem that uses this Struve monotonicity lemma. It's a bit an analogous idea is that when you have like finiteness of some capacity, then you have the almost everywhere existence. That's a bit the Lagrangian version of that. Also, the theorem by Contreras. Tells me that for almost all S below this Magnier, then I can assume that Tn is bounded. And then we have this existence of the periodic orbit. So this is in the exact cases to Contreras. Then this was also extended to more general case by Osuna, Will Murray, and then Asselle and myself. So now here, a bit the important question is how to get the boundedness of the period for a specific S. Now how to get Tn bounded for a given S below Magnier. Okay, so here then the nice story continues with the work of Bari and Taimanov. And then what was their idea? His idea is to get this additional compactness using the index estimate that we know over there, plus some curvature condition. Now, this is like an idea that is kind of, in other settings, is also very much used. If you think about minimal surfaces, it's also used there. And they were pioneering this idea in this case. What was their idea? So the idea is to define some notion of magnetic Ricci curvature. Which in this setting, for us, the Ricci curvature depends on G, beta, and S. It's just a function from the unit tangent bundle into R, such that if the Ricci curvature is bigger or equal than 1 over R squared, some constant, then the period of the limiting orbit in Contreras' argument is less or equal than R times beta times the index of the orbit plus 1. Now this is an argument that is like the prototypical version is the Bonnet-Myers argument. Okay, so so this was a nice approach, but in their case, they defined a version of this Ricci, which was not so natural, and it also was difficult to check when this Ricci was actually positive. And actually, in this range that we're interested in, it was basically, absolutely not clear if this was positive. Also, their argument had some things that needed to be filled. And therefore, we have the next step in the proof, in the story, which is the nice work of Valerio Assenza, which proves a very beautiful theorem that identifies kind of the natural notion of this Ricci magnetic curvature, and then kind of gives a very nice and rigorous proof of everything. So this is theorem by Assenza. It's telling me that there exists a natural notion of the Ricci curvature, magnetic Ricci curvature, and then this has the property that I can write, I have an expansion when S goes to 0. So when S goes to 0, and I look what this is 3 over 4 BQV plus 1/4, squared, plus 1/4 the Hilbert-Schmidt norm squared of BQ. plus lower order term as s goes to 0. Okay? Okay, so in particular, this tells me that at a point where this b is different from 0, then these terms here will approach a positive quantity, which is good in view of this thing. So as a corollary of this, also due to Valerio, is that, again, if Q is compact and beta Q is different from 0 for all Q, so it's nowhere vanishing, then you can find like a threshold S0 and a period T0 such that for all S less than this S0, there exists a contractible magnetic geodesic QS of period Ts less or equal than this threshold T0, and the action is really the action that you see from the minimax. AS QS is equal to DCS, or probably you have also an inequality, I don't remember, but yeah, for the moment I think it's good like this. Okay. Right, and so this is like a very nice theorem, and the remark here is that this theorem was known in the case where beta is symplectic by work of Ginzburg-Gurel and Asher. So if beta is symplectic, then there is a work of Ginzburg-Gurel together with work of Asher that implies the corollary. So this was coming before Valerio's result, and this is also an approach that uses Floer theory. So in some sense, it kind of works a bit more general manifolds, but here you need to require this symplecticity. While this imposes some condition on Q, this condition here, basically, there is no restriction on the topology of Q to get such things. Okay, yeah, and one can think that this is like also in some sense in this spirit, so bounding the index of periodic orbits using some sort of curvature, but it's more like a sectional curvature, while here the advantage of this is that you can use this Ricci curvature, and then this Ricci curvature has more chances to be positive than in this case.
Can you say a couple of things in this Ricci curvature, how it's defined, or is it too technical?
There are several ways to find it. So one way is that you look at the second variation, then after some integration by parts, then you find this this thing, or also from the theory of Jacobi fields. But then you need to look at the restricted equation, the orthogonal, which in this case is a bit more tricky than in the Riemannian case. But then you also, in that case, you find a notional sectional curvature, like, and indeed Valerio has collaboration also with Ivo Terek and Jen Marshall that exploited this in the setting of Jacobi fields and rigidity. Are there other questions? All right. So now I think we are ready to state the main theorem. Okay, so now for the main theorem, you should think that we are going back to a case where Q is also possibly non-compact. And then we have the following statement, and then we give a sketch of the proof. Okay, so the theorem, which is kind of still work in progress, is with Valerio and Leonardo. Okay, so here what I'm doing, I take now magnetic system, QG beta, magnetic system, satisfying two properties such that the first is some compactness property. So the first is that if I look now at the norm of beta as a function here, this must have a strict, compact, local max M, different from the empty set. And what does this mean? Let me maybe say what this means before I go on. So this means that I do first the picture and I write what this means. So that's also even better. Okay, I think I can do the picture here. So if you imagine that this is your Q, and then you have here a compact set M, and then you find a neighborhood, compact neighborhood of this M, I call it W, such that if I now look at the maximum of this beta on W, then it will be M and will be contained in the interior of W. So I have some sort of compact neighborhood such that if I look at the max, it's not on the boundary, it's in the interior, and I call this set of maximum points M. Okay, so I don't know if this is the easiest way to say this, but you have a compact, sorry, you have W is open, compact closure, and then M is the set of points in the closure with the property that the value of beta is equal to the maximum, so to the supremum norm restricted to Wi. Okay, so, and this thing here must be contained in the interior, so in W. Okay, so that's the property. Any questions about property 1? Makes sense? Okay. So then, so this property, I think, is something that one might expect in view of also example 1 at the beginning. Then we need also to assume a second property, which is a bit more technical. And yeah, we are not sure if this can be relaxed or not. We need to assume that beta, the magnetic field, is rationally aspherical near M, which means that yeah, if I integrate beta over spheres in this neighborhood, well, this give me some subset of R, and this subset must be discrete. Okay, so the reason for this you can think is that this gives you a well-defined action, like the one I defined in the exact case, but it gives you a well-defined action up to some error given by the generator of this discrete subgroup. And so therefore, this is useful because we are going to prove the theorem using action arguments. Okay, so these are the two assumptions, and then what is the conclusion is that there exists some T0, such that for all epsilon bigger than 0, there exists some S epsilon, such that if S is less than this S epsilon, then we can find contractible magnetic geodesic QS of speed S, period Ts less or equal than T0, and this Qs is contained in a basically epsilon neighborhood of this capital M. And this is contained in W, but only the part of points where this is bigger than minus epsilon. Okay, so the idea is that the smaller the epsilon, the closer will the orbit be to M. No? So you can imagine here you have this small neighborhood, W beta minus epsilon, and then your orbit will be contained in here. So this is your QS. Okay, that's the statement of the theorem. Any questions about the statement? Yeah. So the second condition is telling me that so if, let's say, U is a sphere, so that, let's say, that exists some, let me call it C bigger than 0, such that if U is a sphere with values in this W, then the integral of over the sphere of beta is actually a multiple of this C times Z. Okay, so if you have a kind of random sphere inside here, then all the integrals that you get are always multiple of some fixed positive value. Right? Either they're all 0, for instance, if beta is exact, or if they are not 0, then they're always multiple of something. Other questions? Okay, so let's have give an idea of the proof. And the proof will be kind of reduction to stages. So the first part I want to do is to do the theorem in the case where Q is compact, when M is a strict global, this time in this case maximizer, and when actually, like in the assumption of Valerius theorem, beta is always different from 0 for all Q. Okay, so in this case I can use Valerius result. I find QS contractible magnetic geodesic with speed s, such that the action of this orbit is actually equal to CS. And remember, by one of the facts, then this is then less or equal than pi s squared divided by the norm of beta plus higher order. And then also the period of these things is bounded, uniformly bounded. Okay, and this works for all s low enough. For all s low enough. So for all s less than s0. Okay, now I want to argue by contradiction and suppose that these orbits are not accumulating here. So I cannot possibly shrink my S0 to get this accumulation of the orbits close to the region I want. So if I argue by contradiction, then I will find some sequence of S going to 0, and the orbits will stay always away from the from the neighborhood. Okay, so by contradiction, there exists some epsilon bigger than 0, and a sequence Sn converging to 0, such that then these QSn are then, so since Sn is converging to 0, these things here are converging to a constant. Because the period is bounded, and they have speed which is going to 0. So then the worst thing that can happen is that these things have length of order Sn. No? Because this is like length is like less or equal than this T0 times Sn, which is converging to 0. And then what do I know about this constant? That this constant must lie in the complement of the neighborhood. So, and what I know is that the value of beta at Q star should be less than beta minus epsilon. Okay, so now these are converging here. So I can now think that they are converging to close to a point. So here my geometry will be kind of the flat geometry, constant magnetic field. So I can have a look at the fact that this might approach then solution in example 2. No? This one where everything was constant. And this is exactly what happens. So if one does a blow-up analysis, what you will see is that actually QSN is not only approximately equal to this constant, but also at the next order, there will be some Q tilde Sn plus OSN, and where this Q tilde Sn is a contractible magnetic geodesic of what system? The system where basically now I'm localizing here. No? So I'm localizing at the tangent space. So the tangent space at Q star, Q, and then the metric is constant. It's just the Riemannian metric at Q star, and also beta is constant. And the speed will be Sn of speed Sn. Okay, so here it's crucial to have this bound on the period to get this compactness property. Okay, so then if we have this property, we can estimate the action of QSN. Remembering that in the example 2, we have a full understanding of the action of orbits. So then this implies that this action here is basically the same as the action, sorry, ASN, is basically the same as the action of the Q tilde Sn plus some higher order. And then this action here, you know that is equal, so it's bigger or equal than pi S squared over the norm of beta. Sorry, not the norm of beta, the value of beta at that point. No? So this was that this is bigger or equal than that was the thing that we showed when we look at orbits of the constant system of the period. And we know that the period is always at least this part here. So therefore, we have this lower bound. And now you know that this is then bigger than the part with the norm, because you are outside this neighborhood. So this follows from this thing here. And this follows from example 2. And this follows from the blow-up. Okay, and then you also know that the last thing is that this thing over here is just the CS. No, CS of CSN. No? And this is like a contradiction, no? with the definition, with the fact that then this must be instead less or equal than, sorry, this must be equal to this CS. Okay, so that ends the proof in this case. Any questions about this? Okay, so then, maybe I have the last 5 minutes. I'll tell you how to reduce to this case number 1. Okay, so so now we want to go from the general case in the theorem, in general, to Q compact and M strict global maximizer. Okay, so it's almost like in case 1, except this part here. So this I will do another, the last step will be to go to that thing. And so here the idea is that, okay, I have the picture over there. So I have the picture of my Q. Here is my M. And then I have here this is my W. And this is the boundary of W. And the idea is to kind of just take this part. So I can assume by wiggling things that this W is really like a manifold with boundary. A compact manifold with boundary. And therefore, what I can do, I can just forget about this part and just double this thing over here. So I can just take the double. And then have, so this is like I double the W, and therefore I get a compact thing which I call Q double prime. Yes, a compact manifold. And then my M will lie in here. And now the idea is that I can extend my beta from this part to the whole double, preserving all the properties that I want, and adding the fact that now the M will actually be the global maximizer for the norm. So what I can do now, I can extend beta to beta double prime on Q double prime. What is the idea? The idea is to take here a neighborhood of the colored neighborhood of the boundary, and then we have a projection from the colored neighborhood to the boundary. And this implies that my beta on this neighborhood by Poincaré lemma is just a pullback of something living on the boundary, beta on the boundary, plus an exact form. And now what I can do, I can interpolate using a slightly smaller neighborhood here. So this would be some n prime smaller neighborhood contained in n, such that I can just now interpolate, and I get that beta with a loss of generality in this smaller neighborhood is just the pullback of this eta. And now once you have this, then you can just reflect everything, and you will get a smooth object on the whole thing. So reflect, and you get beta double prime on Q double prime. And what you can see is that this basically beta double prime will be actually globally now rationally, aspherically rational, no? Because you just did this construction on this neighborhood, and then doubling does not change that thing. And the only thing that it's left to show is that how you define G, G double prime, and then you extend G to G double prime. And then here, okay, this is a metric, so basically you have a lot of freedom, but what you have is that the G double prime must be lambda times G0, where lambda where G0 is some constant, so some fixed metric, and lambda is very large outside M. Because now if you look at the norm with respect to this G double prime, then this will be 1 over lambda times the norm with respect to this G0. So this will be very small. And so this will imply that then now M is global max for this. Okay, then this finishes this part. So we went from the non-compact to the compact case. Okay, then the 1 minute remaining. Can tell you how to go now and achieve this last property of having a beta always different from 0. This is a combination of the transversality argument and a nice trick. So then case 3 is like achieving this beta q different from 0 for all q in the manifold. And then you have basically two cases. So if the dimension of q is bigger or equal than 4, then you know that the rank of the set of two forms is bigger than the dimension of q. And then you can apply Thom holonomic approximation. And you can find beta prime close to beta, cohomologous. And basically beta will be equal to beta prime near M. So then in this case, all the rest, all the properties are still satisfied. And then now if you want to go to the case dimension q equal to 4, so then you have the last subcase. In the case where dimension q is equal to 3, or also when it's equal to 2, if you do this trick twice, you also get this. What you do, you multiply q by S1, and then you take a product metric with a standard metric, and you take the beta prime, the pullback from q of beta. And then if you apply now the theorem, in this case that you already know that it holds, you have that there exists some qs prime contractible magnetic geodesic of speed s near m times s1. And now, since this is a very simple situation, you know that this qs prime t is qst, and then in the s1 component, it's just a linear thing. But now, since this is contractible, this c must be 0, which then will also tell you that this qs is the required orbit. Okay, so I'm really finishing this part, and thank you for the attention.